All right, everyone, welcome back to Etale Cohomology on October 15th. So today we're going to talk about comparison theorems, and then I'll also hopefully get to introducing the fundamental group. So before I do that, are there any questions? All right, so last time I got to the statement of the following theorem. So X is a variety over C. And then we had a diagram of sites. At the top was the analytic étale site of X. So here objects were complex analytic spaces mapping to the analytification of X, so that the map was a local homeomorphism on the source, or a local analytic isomorphism, sorry, on the source, and covers were topological covers. This mapped to the site associated to the topological space underlying the analytification of X. And then this mapped, so we called this map pi, I think. And then this mapped to the usual étale site of X as a scheme, and the associated functor from this site to this site was just analytification. So we called it an. And then the theorem was that pi star induces an equivalence of categories from sheaves on Xn to sheaves on Xn étale. This was an exercise. And then 2 was that an star induces an isomorphism from the cohomology of X étale with coefficients in any constructible sheaf to the cohomology of the analytic étale site with coefficients in the pullback of the sheaf you started with. And then the corollary was that if F is a constructible abelian sheaf, on X étale, then there's a canonical isomorphism sorry, this should be an isomorphism here. There's a canonical isomorphism between the cohomology of F and the cohomology of Xn with coefficients in Fn, where here, what is Fn? So Fn, if you'd like, the short definition of it is pi lower star of an upper star of F. So meaning we start with a sheaf on the étale site, we pull it back to the analytic étale site, and then push it forward to Xn. All right. So are there any questions about the statement? So I'm not going to prove the entire statement today, but I'll sketch an argument when X is smooth and when F is locally constant. All right, are there any questions about that? All right. Well, so 1 was an exercise. So maybe, did anyone do it? And if so, can anyone tell me why it's true?
Given a locally analytically isomorphic sort of map, you can sort of generate a cover by just taking disjoint unions of those sort of the pre-images of those opens where I'm like isomorphic.
Okay, so I think that's a good, so let's actually do it. So in order to prove that something is an equivalence of categories, you have to construct an inverse functor, right? Or at least that's one way to do it. So maybe Ali was starting to tell us how to do that, right? So what we want maybe is given F, a sheaf on the analytic étale side of X, we want some Fn, which is a sheaf on Xn, and then isomorphisms from, for example, pi upper star Fn to F, and also I guess we want to go the other way. So this is if we start on the analytic étale site and go to the analytic site and then go back. So if we start, we also want an isomorphism pi upper star F and with F, or maybe let me call it G. And these things have to satisfy some conditions. So can anyone tell me what this functor is? Like, how do I go from a sheaf on the analytic étale site to the analytic site?
Again, it's just a subcategory. So like the values on the like open sets are just.
So I think what you're saying is we want to construct Fn as just pi lower star of F, right?
Yeah.
Is that right? Okay, yeah, so that's what it means when you restrict to a subcategory. Great. So now can anyone tell me why going forward and backward is the same, or like construct these morphisms for me? Like why going forward and backwards is the same as doing nothing is the identity? Or is naturally isomorphic to the identity functor, I guess? So Ali started sketching the reason. Anyone?
Does it involve some kind of a normal form theorem for singularities?
I don't think you need anything like that. I think it's very, I think this is, it's more or less what Ali said. So if you have let's just go one way. So let's say we have a sheaf up here. So we push forward and then pull back again. So let's just compute the values of our sheaf on some analytic étale open of X, so something mapping to X via local homeomorphism. Well, we can take our thing, which is a local homeomorphism, and cover it by tiny balls where your map on those balls is honestly a homeomorphism onto its image. That's what it means to be a local homeomorphism, right? But then the sheaf condition tells you that the value of F is determined by the value on those tiny balls, and those tiny balls actually live in the analytic étale, on the usual analytic side of X. So that's sort of the reason. So it's really just the fact that a local homeomorphism can be refined into something which is honestly an honest open of Xn. Does that make sense? Does anyone have any questions about that? So the idea is what Ali said. So now refine any analytic étale cover to an honest open cover. And because we're working over analytically, that's something we can actually do. All right. So now let's start proving two. All right, so I claim, so the claim is that it's enough to show that, let's see, what's the right way to say this? That Ri and lower star, well, let me put it this way, enough to show two things. So first of all, there's a canonical map from, I'll be agnostic about which direction the map goes for now, and then we'll figure it out. So there's a canonical map and lower star and upper star F. All right, which way does the canonical map go? It goes left to right, right? So this is an isomorphism. And 2, Ri and lower star and upper star of F equals 0 for I bigger than 0. All right, can anyone tell me why it's enough to show this? Is it clear what the claim is?
So you're going to use the low-ray spectral sequence, which degenerates.
Yeah, so what we want to do is we want to compare, so proof that the claim implies theorem. Is the following. So first of all, we can compute h I plus j, let's say, of x analytic étale and upper star f. So this is what we're trying to compare to étale cohomology. We can compute this, as Bob said, using the Leray spectral sequence as the E infinity page of the Leray spectral sequence, where here we have x étale with coefficients in R, J, and lower star of n upper star F. All right. So this is really just the Leray spectral sequence for the morphism of sites and, sorry about that. Great. So now given the claim, this implies that the E2 page, so this thing, the claim implies that this is just hi x étale. And then, well, when j is 0, we get, when j is 0, we just get f. And then when j is bigger than 0, we get 0. All right. Is it clear that the claim implies the theorem? Does anyone have any, or what are your questions about? I've been told that I'm supposed to ask, what are your questions, rather than does anyone have any questions? So what are your questions about the claim and why it implies what we want to prove? Okay, so then I will move on. Right. So okay. So we've identified the key question is understanding the derived functors of the n push forward here. So let's prove one first. So proof of 1. So we want to prove that the natural map f to n lower star and upper star of f is an isomorphism. So this is the goal. And let's just prove it if f is locally constant constructible. So meaning locally constant with torsion fibers, with finite fibers, sorry. So this, we're just going to prove this special case. All right, so can anyone prove this to me? So what is the key content here? Well, what if f was just constant? Then what would you have to prove? So what are the sections to a constant sheaf? Okay, so first of all, maybe let me remark, we're trying to prove that a map of sheaves is an isomorphism. So that's a local statement, right? Right, that's something we can check locally. So this is in fact, both of these statements are local statements. So this is a local statement. And that means that without loss of generality, well, f is locally constant. So without loss of generality, we can actually assume f is constant.
Sorry, did locally constant constructible just mean you're locally constant and constructible, or
Yeah, that's right.
Like...
It's the same as locally constant with finite fibers.
Okay.
Yeah. Sorry, it's locally constant constructible it's one of these very weird terms where it's very long to say but very short to write. So I think that's why LCC. So I think that's why it's standard terminology, even though it's a weirdly fancy sounding phrase. Okay, so this is a local statement. So without loss of generality, we're actually in the case where f is honestly constant. So then what do we need to prove? Can anyone tell me? So what we want to show is that we have this map from the global the sections of U. So this is some étale open of X, and then let's say just F is the constant sheaf lambda for some lambda, and this map. So this is what the left-hand side is when we take global sections, and this maps to well, what is n lower star of n upper star of F? It's just the same as U n upper star of F. Sorry, n upper star of lambda. Oops. Okay, and it's a formal computation that this is the same as UN with coefficients in the constant sheaf, lambda. All right, so what is the content of this? So here this is the claim that pullbacks send the constant sheaf to the constant sheaf, which is true for any map of sites. Okay, so what is the content of such a map being an isomorphism? So like can anyone tell me what is explicitly gamma U lambda?
So your connected components shouldn't change once you...
Yeah, exactly right. So this is U to this is the lambda to the number of connected components, and this is lambda to the number of connected components of UN. So the real claim is that it's enough to show that the map from connected components of UN to connected components of U is a bijection. Can anyone tell me why that's true? This is not a trivial fact, actually. So maybe let me remind you of the running assumptions in the proof. So here the proof is we're going to assume F is LCC and X is smooth, just to make things simpler. This is substantially harder in general. So can anyone prove to me that for a smooth scheme, the pi0 of the scheme is the same as pi0 of its analytification? Okay, so step one is I first claim, so I claim we can assume U fits into an elementary fibration. So let me draw the diagram and remind you what that said. So here, this is U. This Y is a smooth proper relative curve over some lower dimensional base. And then Z is the complement of U, and it's étale over S, although that won't matter for us. Okay, so suppose we're in this situation. Can anyone tell me what to do? So let's assume this, and moreover, just by dividing into connected components, we can assume U is connected. Okay, so now, so can anyone tell me, let's say, why we can assume this rather than what to do? Any thoughts? So why is it enough? Why are we allowed to? So any open by the theorem we stated last time on the existence of elementary fibrations has a smaller U which fits into a diagram like this, and then the claim is it's enough to prove this for a dense open. So if U is connected and smooth, I claim that U is connected if and only if a dense open is connected. Okay, so this is some point set topology, which you can prove, which I'll leave for you as an exercise. But given your silence, I urge you to either do the exercise or ask me about it now or next time. But given this, so now let's assume that UN, and then hence YN, is not connected. So again, UN is fiber-wise dense, so it's dense in Y. So if U is connected, so is Y. So then this implies that that Y equals, let's say, Y1 disjoint union Y2, where these are the connected components, and these YIs are disjoint unions of fibers, are unions of fibers. Let me call it, this map was called H in the original diagram. H. Well, why is this? Well, this, okay, here you have to prove the theorem for curves. For curves directly. Okay, but we know what the analytification of complex curves are. They're Riemann surfaces, and we know that those are connected if the thing you started with connected. Okay, so now you've written Y is a disjoint union of two things, which are unions of fibers. And that means that H of Y1 and H of Y2 are connected components of S. Why is that? Anyone? Well, H was a smooth map, so flat, so the image of an open is open. It's proper, so the image of closed is closed. So that means image of connected components are connected components. And now we're done by induction on dimension. And I'm sorry, there's some very annoying noise coming from my laundry room. So I'm going to see if I can turn it off so it doesn't keep driving me crazy. I'll be right back. All right, very sorry about that. I hope you talked amongst yourselves. There was something, my washing machine is going, and there was something that was banging on over and over again, which is driving me nuts. So hopefully that's fixed. All right, are there any questions about this statement? So I claim we've now proven that that this map is an isomorphism. So the first statement we wanted to prove.
Is this thing we showed about the connected components always true? Like for more general use? Or?
Oh yeah. This is true for general, more varieties over C. Yeah, so we use smoothness. It's really non-trivial in even for smooth things. Like we use elementary fibrations, and in general, it's even more non-trivial. Yeah. Does that answer your question, Ollie?
Yeah.
Okay, great. Okay, so now let's. Are there other questions? Okay, so now let's prove the second statement, which let me copy and move down here. So now let's prove. So proof of the second statement, which was this. So again, we're going to assume that F is LCC. So first of all, without loss of generality, F is actually constant. Because this is a local statement, and U fits into an elementary fibration again. So what we want is that Ri and lower star of, well, just a constant sheaf, we can say, equals 0 for I bigger than 0. And here, N is the map from the analytic étale site of some U, which lives in an elementary fibration, to the étale site of U for U in an elementary fibration. And okay, great. So this is a big reduction. So okay, so can anyone tell me what we have to prove that this push forward is 0? This drive push forward is 0. Any thoughts?
Could we maybe try to do it on stocks or something?
Yeah, so we could try to compute stocks. So, or in general, we can think of these derived push forwards as the sheafification of the pre-sheaf, which sends an open V of U to the cohomology, right, of the pre-image. So let me kind of state a lemma, which I claim is enough. So the lemma is as follows. So suppose that U is connected and smooth over the complex numbers, and F is LCC on U. Sorry, on U analytic étale. So locally constant constructible on U analytic étale. We haven't said what constructible means, but it just means here I just mean locally constant with finite fibers. And suppose that R is bigger than 0. Then the statement is that for any section in HR on the analytic étale site of U with coefficients in F, there exists some honest étale cover UI to U such that S restricted to UI N is equal to 0. So in other words, we can kill analytic étale cohomology classes with honest étale covers. Okay, so more or less what this is saying is that, well, when we compute the stalks of this push forward, we'll be taking these groups and then taking the limit over small and smaller covers. So this is exactly, this lemma is saying, so the corollary of this lemma, so the corollary of the lemma is that the stalks are R of n lower star f at some x bar equals 0, because any section of the thing we're taking the sheaf associated to, namely this thing, will be eventually killed by some honest étale cover. Okay, so and this implies, of course, that R n lower star of f equals 0, which is what we wanted to show. All right. So
Can I ask a quick question?
Yeah, go ahead.
So the reason you're placing emphasis on honest étale as opposed to just, I'm guessing this is always true for like analytic étale covers?
Yeah, I mean, so if you take a locally constant sheaf, it's locally just a constant sheaf. So it's enough to show you can kill the cohomology of constant sheaves by passing to a small cover, but just take a cover by balls.
I see. Okay.
Yeah, so it's this doesn't tell you anything, or it doesn't tell you anything interesting if you let these UIs be any analytic étale thing. The point is that these have to actually come from algebraic objects. All right, so I claim this lemma, and why I just explained why this lemma implies the theorem. So let's prove the lemma. All right, so can anyone help me prove the lemma?
Maybe go look inside our sort of elementary fibration and try to prove it for curves.
That's a great idea. Yeah, so let's do it. So as before, with that also generally, U sits in elementary fibration. So let me write it out, and this time I'll label all the maps. So here, this was J, this was I, this was H, this was F, and this was G. And I'll just say it all again. So Y is a smooth proper morphism with fibers of dimension 1. J is an open embedding, I is the closed complement, G is finite étale, and J also is fiber-wise dense. In the image of J is fiber-wise dense in Y. All right. So what we're going to try doing is we're going to try taking, we're just going to try to compute what we're studying here, namely this group here. So this group, so we have S, which lives in HR of U analytic étale with coefficients in F. And we can compute this group using the Laurier spectral sequence, as always. So this is given by HI of S with coefficients in RJ, F lower star of F, where here I plus J equals R. All right, so now what? So we have this class here. We can just choose some elements here, which give it to us eventually, or which give its associated graded pieces in the filtration on the E infinity page of the spectral sequence. So so what? So what now? So there's two things we could try to kill. So we could try to kill these sheaves where J is bigger than 0. So that's something that induction should allow us to do. And then we could try to kill these cohomology groups. So let's try it. So first of all, I claim, so RJ F lower star F is the sheafification of some pre-sheaf that V goes to like the J, I guess, of F inverse V, F, right? Do you guys agree with this? Great. Okay, but these are groups that we can kill by passing to a cover, or at least we can kill any element of them. So so by the induction, okay, and we haven't done the base case of this induction yet. By induction, we can kill the contributions coming from Rj F lower star F for J bigger than 0. Okay, so now we're left with, so given that, we're left with contributions from hi of S with coefficients in, sorry, well, now we can assume J is 0, so now we just get F lower star of F. Okay, what now? So we want to kill some stuff in these groups. So can anyone tell me maybe anything about this sheaf F lower star of F? Anything? Okay, so let me remind you, the point of it, oh, here we are. The point of an elementary fibration was that the fibers of this map have constant topology. So this a priori crazy sheaf is in fact LCC. Okay, so here we're in the same situation we started as. We want to kill classes in the cohomology of an LCC sheaf on a smooth S, except S has one dimension lower. So again, we're done by the induction hypothesis. Okay, so now I claim we're done with the proof except for the base case. So done with the done except for the base case. The base case where the dimension of U equals 1. All right. Does anyone have any questions about this induction step?
Could you explain again why F lower star F is LCC because of the elementary fibration part?
Okay, yeah. So this is here. Maybe let me be clear about where I'm actually computing things. So here, F was a locally constant sheaf on the analytic Etale site, and this is an analytic map. So this is a computation in singular cohomology. So what you do, so how do you compute this sheaf? You take a small open on S. You can assume it's just a tiny ball. What was an elementary fibration? The defining property was that this F was given by taking a family of Riemann surfaces over a ball. Well, once I've replaced S with a tiny ball, and then deleting the same number of points from each fiber. So what I have is now a trivial family of punctured Riemann surface, like a punctured Riemann surface bundle over a ball. And that's something that one can compute the cohomology of directly. In fact, it's going to be homeomorphic to just a punctured Riemann surface times a ball. And so it's just the same as computing the cohomology of a punctured Riemann surface.
Thanks.
Yeah, great. Yeah, so this is a topological computation. So I know a couple people in the class aren't as familiar with singular cohomology, and if that's the case, you just have to take my word for it. That's a kind of classical computation. All right. So can anyone help me out with the base case where the dimension of U equals 1? So now what do we have? So we have F which is in U analytic étale. Oh, sorry, it's a sheaf on, it's a locally constant sheaf, LCC sheaf, on the analytic étale site of a Riemann surface. So this is a Riemann surface now, which we're thinking of as the analytification of an algebraic curve, and we want to kill cohomology classes in HI U analytic étale F. And what do we have to do this? We have to do this for I equals 1 and 2. So we know from topology that the higher cohomology of Riemann surfaces with cohomology and locally constant sheaves vanishes for I bigger than 2. All right, so let's do it. So what if I equals 2? So we have to kill this by passing to honest, like algebraic étale covers of U. All right, so how are you going to kill cohomology in degree 2? So okay, if you'd like, you can assume F is the constant sheaf, right? Because again, by passing to a cover, you can make it constant. So how do you kill H2 of a Riemann surface with constant coefficients? So I want you to give me a cover of an algebraic curve so that when you analytify, there's no H2 in singular cohomology.
So it is embarrassing, but I've forgotten, what is H2 of a torus?
Well, the H2 of any compact Riemann surface is one-dimensional. But the word compact there is key. So I claim if you pass to any affine cover, so I claim that affine curves have no, affine complex curves, so Riemann surfaces minus at least 1 point, have no cohomology. Okay, and why is that? Well, a Riemann surface, H2 is always, if you have a compact Riemann surface, H2 is always one-dimensional, and then deleting a point that kills the generator of that thing. So if you'd like, it's generated by the Chern class of the line bundle associated to that point. And so once you delete the point, that Chern class goes away. If you want to think about it topologically, you can just think about it in terms of honest surfaces. So how do you make a surface? You take some polygon and glue the opposite edges together in some way. Okay, but once you delete a point, you can just contract this polygon. You can just deform this polygon back onto the boundary. And that's a one-dimensional cell complex. So it has no higher cohomology. Okay, so that does I equals 2. Okay, are there any questions about that? So now we have to do I equals 1. So how do we kill? So we have S in H1 of the analytic étale site of U with coefficients, let's say in some constant sheaf lambda, and we want some UI to U, an étale cover, such that S restricted to UI analytic étale equals 0. So how do we do that? So here, this is actually the first place that a real theorem in complex analytic geometry shows up, and the only place in the proof, basically. I mean, arguably the I equals 2 case from before used the cohomology of a Riemann surface, but it's not too bad. So how do you kill a class in H1? So this is something we learned when we were studying torsors. So how do we think about S geometrically?
Is there a picture you could draw that maybe we can keep in mind?
Sure. A picture I can draw. Well, I guess I would say, so here S corresponds.
Are we going to sort of use the sort of torsors or trivial over from self sort of?
That's exactly right. Yeah. So S corresponds to some lambda torsor over U analytic étale. So what is that? That's a covering space of U with Galois group. Sorry, U analytic étale, or UN with a Galois group lambda. Okay, so the claim, so I guess that was the picture I was going to draw, is that you know, S kind of gives you some kind of covering space. This is supposed to be some kind of picture of a unramified covering space, although I don't really know how to draw that. So the claim is that there's equivalence of categories. So this is called the Riemann existence theorem. So the claim is that there's an equivalence of categories between finite étale covers of U and let me call it finite analytic étale covers of U. So this is finite covering spaces. Okay, and the hard part is, yeah, so if U was proper, this would just be, or if U was projective, sorry, this would just be, so this would, so maybe I'm not going to prove this, but let me just make a remark on it. So remark, if U is projective, this is just immediate from Gaga, from Serre's Gaga theorem. I mean, that doesn't mean it's easy. Serre's Gaga theorem is non-trivial. So but the hard part is dealing with the case where U is open, and what you do is the content is to show that any finite analytic étale cover of a open subset of the analytification of algebraic variety extends to a ramified cover of a compactification. So that's somehow the content of this theorem. Okay,
Could you repeat that last thing? Sorry.
Yeah, so the content is to show, so this is in the normal setting. So it's to show that if you have the analytification of a normal variety with some compactification X, then any finite étale cover of that thing extends to a possibly ramified cover of the compactification. So the proof of this passes through proper varieties. Does that answer the question?
Yeah.
Great.
Can I ask a quick question?
Of course.
So I'm wondering how to interpret this. So does this mean that if we have some kind of complex thing that came from an algebraic variety and we have a covering space of that,
Finite covering space,
and we can give equations to the thing on top, to the covering space, which makes the covering map algebraic?
It makes both the covering space and the map algebraic.
Right, both of them algebraic.
Yeah. So for example, if you take P1 minus 3 points, that has a really big fundamental group. It's I guess complex analytically, it's free on 2 generators. So okay, to write down a covering space of P1, like a finite covering space of P1 minus 3 points, you need to write down an action of the free group on 2 generators on some finite set. And the corollary of this theorem is that any such action comes from an honest algebraic curve mapping to P1 minus 3 points.
Oh.
Yeah, so that's at least part of the content. So it says, in particular, coverings of complex algebraic curves can be written kind of purely in terms of this group theoretic or combinatorial data.
And so is there like some kind of moral reason why this doesn't happen for like C covering C mod lambda, like an elliptic curve? Because I understand.
Like why you need finiteness?
Yeah.
Yeah, I mean, it's sort of this fact I was saying about extending to a proper convectification. So the reason is that map, so like the I guess the Weierstrass P function or whatever, has essential singularities at infinity.
Cool.
Yeah, or I mean, the simplest situation is if you put the map C to C star, right? So that's you might guess, you might like ask, does that come from a map like from A1 to GM, right? Okay, and of course it can't because it is infinite fibers. But like the reason that this proof doesn't work is, okay, what is that map? It's the exponential map from C to C star. So that's e to the x. And so if you were to try to apply this theorem, you would want to say, well, does that map from C to C star extend to a map from P1 to P1? Right? That's the kind of compactification you need to apply the argument here. And the reason it doesn't, again, is that the exponential has a essential singularity at infinity.
Cool.
Does that make sense, Artin?
Yeah, it does. I mean, it's just, just philosophically speaking, it's sort of like this, there's something transcendental about the map.
Yeah, that's right. So what I would say is, I mean, my thinking about this is that like anytime you see a theorem like this, like a correspondence between an analytic object or a formal object, like a formal scheme or a rigid analytic object, and algebraic objects, it should be a miracle, right? Like if it's true for non-proper varieties. So one expects in general for proper things the behavior to be the same, but precisely because of this issue of kind of essential singularities, like you just don't expect this to happen for non-proper varieties. And then here the miracle is that this finiteness lets you reduce to the proper situation. Okay, so let's apply the Riemann existence theorem. So let me remind you, so we had S in H1 of the analytic étale site with coefficients and some constant sheaf lambda. This corresponded to some US to U, which is a finite local analytic isomorphism. Okay, and then Riemann existence, sorry, this should be UN. So Riemann existence, so this claim I just stated implies that US is the analytification of some V, and moreover, it's an analytification of a diagram like this. Okay, and then that's what we wanted to prove. So then S restricted to V is 0 because, Vn, because torsors kill themselves, kill the corresponding cohomology classes. So here, the point is that US is a lambda torsor, and we had this fact from earlier that if you take a cohomology class in H1 and pull it back to the torsor that defines itself, it dies. All right, so that's the proof. Are there any questions about that? All right, so that was pretty cool, I think. All right, so just to recap, we can now compute a lot of examples. So just as an example, I mean, and maybe it's worth mentioning, like this is like how maybe even the vast majority of computations of étale cohomology are done, is by reduction to the complex world. So just as an example, what's your favorite variety? Anyone? That's not a curve. Okay, no one has any favorite varieties, but just as an example, if you take a K3 surface over C, so HI, so let's suppose X is HI of X étale with coefficients in Z mod and Z, we now know by an analytic computation is z mod nz for I equals 0 or 4, 0 for I not equal to 0, 2, or 4, and z mod nz to the 22 for I equals 2. Okay, and what's the proof of this example? It's, well, we're over C, and we can compute this group by analytifying and then working with complex K3 surfaces. Okay, and it's, what? I'm sorry?
Oh, sorry. I just wanted to ask if a Hodge structure also carries through to the étale side, like in a nice
So the
way.
Hodge structure doesn't really make sense here, because here we're taking Z mod NZ coefficients, and Hodge
Yeah,
structure.
but like if we were taking like C coefficients or something like that.
Yeah, but the theorem was only for locally constant constructible things, which are torsion.
Okay.
And in general, we'll really never take étale cohomology with coefficients and things that are not more or less torsion. So I mean, we'll do things like GM, which I guess is an algebraic group, but in general, we'll be doing things like Z mod NZ, and then shortly, probably next class period, I'll talk about how to get something which is more characteristic 0. But what it'll be is we'll take Z mod L to the NZ and then take the inverse limit over N.
Okay.
So it's
Yeah,
still,
okay, that makes sense.
cohomology is always built out of torsion things. And the reason is actually, I mean, the reason why we can compute is precisely this theorem, which is that we needed finite here. Right. So if you had Z, and we already talked about examples of, so just as an example, so non-example. So if you take x equal to GM over C, H1 of x étale with coefficients in the constant sheaf Z is 0, whereas H1 of xn Z is 1. And well, why is that? Or sorry, it's not 1, it's Z. And why is that? Well, it's we just talked about it. So an object here corresponds to a Z torsor over GM, right? So there is one analytically, namely the map from the exponential map from C to C star, but that's not an algebraic object. So okay, that's not actually a proof of this equality, but at least it's an explanation for why these two things aren't equal. Does that make sense?
Yeah.
Great. All right, so now I want to start talking. So we've now compared cohomology. I want to talk about the other kind of homotopical information that we can understand in this course, which is the fundamental group. So this is going to be about étale fundamental groups. So we're finally at the point where we can actually say something about these, which is why I'm defining them now. Milne defines them very early in the exposition, and I've rearranged some things to avoid talking about them until now, when we can actually compute some examples. So okay, so here's the definition. So here X is going to be a scheme. Let's say what do we actually need? So what we need is a locally Noetherian scheme. And X finite étale will be the following category. So this will be the category whose objects are Y to X, which are finite étale. So objects Y to X finite étale, and morphisms are morphisms over X. All right, are there any questions about this? So maybe a remark is that this is a site. I mean, so with covers, just topological covers again. This is a site. Okay, but if X is connected, all morphisms are covers. Okay, and it's an interesting site, which we'll talk about in a second. Okay, so here's the definition. So let X bar, let x bar be a geometric point of x. Then there's a functor fx bar from x finite étale to sets given by sending y over x to the fiber of y over x bar. So this is actually a functor to finite sets, right? Do you guys agree with this? So it's a map functor to finite sets because here we're looking at finite étale morphisms. Okay, and then the definition of the étale fundamental group of x at the base point x bar is automorphisms of this functor fx bar. Okay, and just a terminology, this functor is called a fiber functor. All right, and we're going to give this a topology. So this is a topological group. And it's given with the topology, the maximal one, such that the maps from pi1 étale xx bar to aught of fx bar of y, so this is aught of some finite set, is continuous for all y. All right. So this is the definition of the étale fundamental group of a scheme. Are there any questions about the definition?
Should that be the coarsest topology?
Yeah, you're right. Coarsest topology. So yeah, I guess I didn't say what minimal means, but the coarsest topology, or what maximal means. Yeah, so the coarsest topology is such that this is true. So the fewest open sets making this true. And here, these are just symmetric groups. These are given the discrete topology. Okay, so explicitly what this means is that that for any element of one of these, so any element of one of these symmetric groups, any automorphism of one of these fibers, the preimage is open. That's explicitly what the definition tells us. All right, are there any questions about the definition? All right, so let's do an example. Let's do the case where x equals spec k. So then what's a geometric point? So let's take x bar to be a map from spec k bar to spec k. And what are we doing? X finite étale is the category of finite separable extensions. L over k, or really the opposite category. All right, so can anyone tell me what is the fundamental group?
Going to be the Weil group.
Yeah. So it's the fundamental group of spec k, with coefficients in our x bar is, well, it's a little bit subtle. So what it is the Galois group. I mean, so here in general, the Galois group involves a choice of separable thing, right? But it's the absolute Galois group of ks over k. So you have to think about how to get a separable extension from a map like this. All right. So this is an exercise which is worth working out. It really is. It's really just restating the main theorems of Galois theory. There's no real content here, but it's worth doing. All right. Let's do another example. So suppose that X,
Doesn't X finite étale also have disconnected covers?
yeah, so it should be finite separable, you're right. So finite separable, not extensions, but étale. So finite étale K algebras. That's right. But any such thing is a finite product of finite separable extensions, which means that if you know what this group does on the finite separable extensions, then you know everything. Yeah, that's a good call. Thank you for that correction. All right. Are there any other questions about that?
Thinking about the case where K is a finite field,
Mm-hmm.
then one knows this to be then the profinite completion of Z, but inside it is there's the Frobenius with dense image powers. So is such a thing of any importance?
Like the Galois group, like is Frobenius important?
Well, obviously it is, but the question is it somewhat general? Is there sort of a case of instead of profinite stuff, there's a dense free stuff or anything like that?
It's typically it's sort of rare. I mean, I'm about to describe a situation where it happens, but I mean, like inside of the Galois group of Q, for example, is it the naturally the profinite completion of some discrete group? Like I don't think so. And I think provably, if you take a curve over a finite field, you can take its fundamental group, and I think provably that's not the profinite completion of a discrete group. Although I would have to check that. I think I see a proof, but I don't know a reference.
Okay.
Yeah, it's so just I mean maybe let me just kind of. Yeah, maybe before it's actually worth doing a couple. Maybe let's do a couple. I was going to give you some nice examples first, but let me give you some mean examples. So here's some kind of example. So let's take. I don't have quite enough to do this example yet. Okay, so I'll just tell you some facts, and then we'll prove them hopefully next time. So if we take A1 over a field K where this has characteristic P bigger than 0. So this is not topologically finitely generated. For any field of characteristic P. And the reason why is that there are too many covering spaces. So we already computed this. So the Etale cohomology of A1, with coefficients in FP, and this was the co-kernel of K adjoint T maps to K adjoint T via the map, via the Artin Schreier map, X goes to X to the P minus X rather. Okay, and this co-kernel was huge. Okay, but what is this set? This is the set of FP covers. So it's saying there's an unbelievably huge number of covers with Galois group FP. And if you explicitly work that out, what that says is that, so this group, and we'll talk about this more next time, is the abelianization of the Etale pi 1 of this with any x bar, abelianized and Hom from that into FP. So in particular, if you Hom from a profinite group into a discrete group is not finitely generated, then into a finite discrete group is not finitely generated, then the profinite group must not have been topologically finitely generated. Okay, here's another example. Let's suppose E is an elliptic curve over K is K bar, where the characteristic of K is P bigger than 0. Well, Etale pi 1 of an elliptic curve, we're going to see, I'm going to suppress the base point for now. We're going to see is going to be the same as the Tate module. So it's the inverse limit over all n of En. So what is this thing? So this is ZP times the product over L not equal to P of ZL squared for E ordinary, and the product of ZL squared for L not equal to P for E super singular. Okay, but in particular, if you just stare at this for a minute, like what kind of group would you have to be taking the profinite completion to get something like this? You would want it to be Z squared, right? But here you have the kind of rank of what you get here depends on whether you take the pro L completion or the pro P completion. So I think this is already enough to see that there's no at least natural discrete group you're taking the profinite completion of. Okay, and maybe I'll just finish with the example I was planning to do, and I'll explain why this is true next time. So the example is that if X is normal over the complex numbers, then the étale n connected, then the étale pi1 of X with any base point X bar is isomorphic to what you get if you take the complex analytic space associated to X, take the appropriate base point, and then take the profinite completion. So in the complex setting, these things, Bob, are indeed profinite completions of natural discrete groups, namely the fundamental groups of the analytification. All right, I'm out of time, so let me stop recording.